Okay, for our introduction to exponentials, we have two sequences that we're going to look at. It says, consider the sequences below, determine which is arithmetic and which is geometric, and write the recursive formulas for each. This is a little bit of a throwback to earlier on in our year. So this first sequence, if I'm trying to figure out the pattern, I might try to see if I can add something, subtract something, multiply, divide. And I see that it's decreasing, and it's actually being cut in half over and over, so I know that that is times a half, times a half, times a half. Okay, that means that this has to be geometric, because geometric sequences are multiplication or division. It's got a common ratio. So for this problem, our recursive formula would be a sub n equals, because that stands for any number that you want, found by taking the number before it and multiplying by a half. Okay, over here, this sequence I see is also, oh, it doesn't decrease actually, it's increasing, but this one is increasing by addition. So we've got a common difference that's being added over and over, so that means this is arithmetic. Arithmetic is when you add or subtract over and over. So this recursive sequence also starts with a sub n and a sub n minus 1, but the thing that I'm doing to the term before over and over is I'm adding 30. Okay? Now, what I want to pause and take a moment to explain is that when we first learned about these two sequences, we hadn't learned about exponentials, quadratics, or linear functions yet. We just talked about number patterns. But now we know with arithmetic, this is the same as a linear function, okay? Because you're adding 30 over and over, that's your slope. It's just increasing by 30. If I was to graph this, it'd be up 30, up 30, up 30, up 30, up 30, right? Well, this one over here is not linear. If I was to graph this, it'd be looking, let's see, it's increasing. It looks something like this. It would get steeper and steeper, and it's curving, right? This actually isn't quadratic. This is actually exponential, as you can tell by the title of this whole unit. So geometric sequences are very closely tied to exponential functions. So let's look at this example. It says a ping pong tournament began with 64 competitors. Complete the table below, assuming if a person loses their match, they're eliminated from the tournament. So at the beginning, round 0 of the competition, we have 64 participants. After the first round, half of them have lost. We have 32 remaining. That pattern is going to continue where half of the people are eliminated over and over and over until round 6, we have our winner, right? We could keep going by cutting this in half as well, but we don't have 0.5 of a person, right? So really, at round 6, we have our one winner. So let's put these points from the table on our graph. 0, 64, 132. As usual, my board is a little off. Okay, and you can see, again, the curved points that is really steep at one point and a little bit flat at the other point, right? Now, if this was quadratic, it would curve right back up this way, but it didn't, right? It just stopped at 6. So, just what function family does this belong to? It's exponential. And it says how many rounds does it take before the tournament's over? 6 rounds. Because the 7th round would mean there's only one person to play. Now, going back to the fact that this kind of looks like a quadratic, let's explore why it's not. So we're going to sketch these graphs from these tables and then note what the function is. So 0, 3, 1, 6, 2, 9. Again, I'm just sketching. There's those points. Well, that is a linear function. So the parent function would be y equals x. And again, I can further tell that by looking at my table. This is plus 3, plus 3, plus 3, plus 3. That's a common difference. It's a slope of 3. So this middle one, same thing. Let's graph it. 0, 1, 1, 2, 2, 5, 3, 10, 4, 17. This thing is curving up like this, right? I'm going to hold off on putting quadratics. That might be exponential. I don't know. This last one, 0, 1, 1, 3, 2, 9, 3, 27, 4, 81, way up there, right? So again, curving up. Those look very similar, right? So let's explore the tables a little bit. Well, this one right here, if I was to try to do this, I'm first going to see if I can add, subtract, multiply, or divide. Well, to go from 1 to 2, that's times 2, but that's not how you go from 2 to 5. So, okay, maybe it's something different. Maybe it's multiplication, no, addition, no, subtraction, no. I can't find anything that's happening over and over. So let's just look and see what is being added. This is plus 1, plus 3, plus 5, plus 7. Well, I actually have a pattern here. This is plus 2, plus 2, plus 2. This actually proves to me that this is a quadratic because, we haven't learned this yet, when you have a double common difference like this, it's quadratic. If there's no constant slope, but if you go to check the common difference again, you do get the same number, that is the clue that it is a quadratic function, okay? Exponentials, this last one does not have that. What it has instead is a common ratio, something that is being multiplied or divided constantly throughout the entire table. So in this case, it's times 3 over and over and over. So this one is an exponential. And it does not have that double common difference. Parent function, remember that there isn't a parent function for exponentials. There's just the orphans. They don't have a parent to report back to. It's just a whole bunch of random exponentials. So it's kind of a trick question down there. So going back to this ping pong tournament thing, again, the reason we know this is quadratic and not, the reason we know this is exponential and not quadratic is because there is a constant ratio here where we're multiplying by a half over and over. There's no double common difference here. Okay, so let's try this again. It says consider population of bunnies. If there are initially 3 bunnies, so that's times 0, there's 3 bunnies, and each of those has 2 bunnies of their own. So these 3 bunnies each have 2, so I've got 6. And that trend continues, so each of these 6 bunnies each has 2. And each of those 12 bunnies has 2, etc., etc. They want to know how many bunnies will there be after 5 generations. Well, 96 bunnies, right? So let's graph this and see what this looks like. Don't know my board. Let's see what can that's better. 6, 212, 324, 448, 596. So again, you can see this curving graph. If we're trying to figure out if it's quadratic or exponential, we just look to see what our table shows, what the numbers are doing. This is multiplying clearly by 2 over and over. So this is exponential. Okay, how do I know? Because there is a common ratio. There's something that's being multiplied over and over that's common. How many bunnies will there be after 8 generations? Well, you can just keep that pattern going. If at 5 there was 96, well then I double it again. So 6 we would have, let's see, times 2 would be 12, 192. So then 7, change colors here, 7, multiply that by 2, we'd have, let's see, it's almost 20, it would be 496, 384. Is that correct? Yep. So then 8, our winning number that we're looking for. Let's see, 4 would be 8, and 768. That's how many bunnies we'd have, just 8 generations later. People say they're reproducing like bunnies, it means there's a lot of bunnies. All right, so number 8 says look at the first 3 terms of the following pattern, and then we're going to complete a table. So it says the first term has 2 blocks. I'm going to put that actually right here. The second term has 4. This third term has 8. So I can kind of see the pattern here already. Times 2 times 2, so this would be 16, 32. But then going backwards to the 0 term, if I would divide by 2, it would start with 1 block. And now put these on my graph. It's not numbered, but just assume everything is counting by 1. So 0, 1, 2, 4, 8, 16, 32. I had to count all those out. And again, you can see that curve where things are getting really steep. That's an exponential. So when it says how many blocks would it take to build the 6th term, again, you can just keep this going. The 6th term would give us 64 blocks because it would double again. Okay, now here's where things get a little bit interesting. Here's where you're going to need your calculators. So if the equation y equals 2x represents this function, 2 to the x, sorry, how many blocks would it take to build the 12th term? Well, the 12 here is like my x, my term number. So I've got 2 to the 12th power. Now, luckily, we have calculators where you can just type that in to the run matrix screen, or if you have any other calculator really, you should be able to type in an exponent of 12 and calculate it. What you'll see here in a second is that we're going to run into a stumbling block where you can't just type it in. You're going to have to actually use the graph menu to figure it out. But again, for now, just type it into the run matrix screen on your calculator, 2 to the 12th, and you should get 4,096. Now, you could also do that by continuing this pattern all the way down. What you cannot do is think about it proportionally. For example, the 6th term had 64 blocks. So the 12th term, some people think you would just need to double it. Like, oh, well, 6 to 12, that's just doubled, so 64 doubled, but that's not the case. The 12th term, well, that means we've multiplied by 2 over and over and over until we got to the 12th term. So it's not quite that easy. Okay, same thing with this 19th term. That means that we need to calculate what is 2 to the 19th power. You just type it in, 2 raised to the 19th power. Use that little up arrow, the little caret, to type in the exponent that you want. We get 524,288. Now, here's where things get interesting, which is what I was talking about. It says, using the equation, if 65,536 blocks were used, what term would this represent? So what we've just been given is the y. We are trying to figure out what x is, and x is the exponent. Well, there's no way to work backwards here. There is, but you won't really learn it until Algebra 2. So we can't just divide by 2, right? We can't cut things in half. We actually can only use our calculator. So what we're going to do is we're going to go to the graph menu in our calculator. We're going to type in y equals 2 to the x, the equation that we have. Then you're going to draw it, okay? What you should see is a pretty little exponential. If you don't, feel free to adjust your window or zoom in and out. Then what you're going to do is you're going to use that G solve button, our favorite button. When you do that, you're going to see a bunch of options. But what you're going to need to do is press F6, which has an arrow above it. Looks like this, almost looks like a play sign, to see other options. And you're going to choose XCal. What that stands for is X calculate. Well, we're trying to calculate this X right here. So when I press XCal, it's going to say, okay, enter the Y value. Well, the Y value they gave us was that 65,000 number. So when you type that in and press enter, it'll either tell you the answer or it'll say not found. If it says not found, that just means that you need to zoom out quite a bit more because you're trying to tell the calculator to search something way up at the 65,000 mark. So you may have to adjust your viewing window or zoom out until you get to that point so the calculator can see it. So again, we are doing XCal, typing it in, and you get x equals 16. Okay, but again, there was no way for us to just work backwards and solve that by like dividing by 2. You had to actually go through your calculator and do those steps. There's really no other option. But we'll be practicing that a lot. So here's some other options. These have nothing to do with the block problem. It's just random equations to work through. It says if you've been given y equals 2 times 3 to the x and x equals 7, well, I can type that in. I can type in 2 times 3 to the 7th power. The next one, they give me the y, 354,294 equals 2 times 3 to the x. They want to know x's. Well, that one I can't do unless I put it in the graph menu. So basically, if you're looking for x, you have to use the graph. If you're looking for y, you could just type it in. Okay. So number 11, again, they've given you y. You're looking for x, you're going to have to use your graph. The last one, though, they give you x, so it's just negative 4 to the 7th power. You just type that in. Okay, I'm going to go ahead and pause it. I'm going to let you kind of play around a little bit with your calculators and try to figure it out, and then we will go over it together. Alrighty, so there's your answers in red. Again, if this is something that is kind of confusing to you, I'm not really able to show you my calculator as I'm doing this, but I'll post a different video that shows you how to do this in your calculator so that you can watch that if you're struggling. But again, there's no other way to do this other than using your calculator. If there was, I would tell you. Obviously, with a problem like this, you could literally take negative 4 and multiply it times itself. Then multiply negative 4 again, and keep doing this until you, keep doing that until you get to it 7 times, but what's quicker is just to use your calculator. Alrighty. So that is all for Introduction to Exponentials. So you do have a homework assignment. It's real quick and short, just to kind of recap everything we've done today. But make sure you ask me if you have questions.